Okay, let's get started. Welcome to the Stanford Digital Economy Lab lunch. Our speaker today is Eduard Talamàs. Eduard is a professor of economics at IESE Business School in Barcelona and a research fellow at the Center for Economic Policy Research. His research focuses on the economic effects of AI, organizational economics, bargaining, and network markets. He earned his PhD in economics from Harvard in 2017, where he was mentored by Ben Golub, who you may remember from one of our earlier talks. After he got his doctorate, he was a postdoc at the Warren Center for Network and Data Sciences at the University of Pennsylvania. In 2022, he was recognized as one of Poets and Quant's best 40 under 40 MBA professors, highlighting his impact on both economic research and MBA teaching. So we welcome and encourage questions during the seminar. If you're in the Zoom audience, please submit your questions using the Q&A function there on your Zoom. For those of you who are here at Stanford, just raise your hand, and when we call on you, we'll bring you a mic over. Please speak into the mic and repeat the question so everybody can hear you. Eduard, welcome to Stanford. Please tell us about AI in the knowledge economy.
Thank you so much, Eric. Thank you for having me and for this nice introduction. I'm very, very excited to be here telling you about joint work with Enrique Ide. Enrique is a fantastic economist, also in IESE Barcelona, and I'm super excited to be working on this with him. What's the idea of this project? Well, we have this goal of building a framework that contributes to various things. The first one is organized discussion about AI's labor market impact. Second, guide empirical analysis. Of course, there's a lot of empirical analysis needed, but there's also being such a new thing, I think we need some guidance for that. And third, guide policy. There's a lot of interest in regulating this technology or thinking about perhaps regulating or being ready to regulate. We want to guide that as well. Why do we think this is needed? Well, the first thing we have to ask is, how is AI different from previous automation? Why that matters? We want to say something about that. The second one is, what determines who is complemented and who is substituted by AI? I think this is a fundamental question that a lot of people are asking. We want to give some guidance about that. We think this is particularly important because there's seemingly contradictory evidence on this point, on who wins and who loses. For example, there's many examples, but let me just give you two. Eric's recent paper with Lee and Raymond is forthcoming at QJE this year, suggests that AI benefits the most knowledgeable the most. Right? But there's this other paper that recently came out, which is now R&R at QJE, which says exactly the opposite in another setting. Right? So there's this seemingly contradictory evidence that we would like to understand, we would like to make sense of. Can we rationalize this evidence? What new data do we need to collect to sort of make sense of that? Finally, what are the effects of regulating AI's autonomy? So my promise to you is that in the next 40 minutes or so, I'll give you answers to this, or our answers to this. So let's get started. What is the fundamental difference between AI and previous automation technologies? It's the idea that it can do cognitive, non-codifiable work. Okay? This sets it apart from other technologies like enterprise software, which would do cognitive work, but mainly codifiable. What is codifiable knowledge? Is that kind of knowledge that you can put in a recipe or you can put in a list. You can essentially write down how to do something. But we know, at least in Spogliani, in the 60s, that a big part of knowledge is actually non-codifiable. We know more than we can tell. So the new thing about AI relative to other cognitive automation that has come before is the fact that it can do non-codifiable work. Okay? And similarly, traditional robots will do manual work that is also codifiable. Those are the traditional robots. I was just talking with Eric about the possibility of physical AI, this idea that we'll have robots that can actually do non-codifiable knowledge as well. That seems to be a little bit further in the future. So we'll be focusing here on AI that can do cognitive, non-codifiable knowledge. Did I do that?
AI doesn't.
Yeah, exactly. Oh, that was easy. Okay, so coming to the Digital Economy Lab to tell you what's different about AI seems like giving a sermon to Buddha, right? Like Eric Eric and Tom have been saying this forever. So I think we have something. This observation is, of course, not new. They've been saying this for a long time. Now, what we think we have something new to say is about why is this difference important, okay? And this is the observation that non-codifiable knowledge is a major economic bottleneck. And there's a whole literature studying that. There's a whole literature studying how we organize work that requires non-codifiable knowledge. What's the idea? The idea is that being non-codifiable, this knowledge is very hard to transfer across individuals. As a result, we have all these different individuals that know different things. It's very hard to communicate this knowledge. The knowledge that an individual has then is constrained by her time. And as a result, we need organizations to structure the workflows in a way that everyone is using their knowledge in the best possible way. Okay? There's a whole literature studying how we organize, how a major thing that organizations do is to put things in the right place and put structures around the people who know most to use their knowledge efficiently. Why do we need to do that? Because the vast part of the valuable knowledge is non-codifiable. Okay? And our observation is that if AI can do this kind of work, and combined with AI scalability, that should lead to a reorganization of the economy. If a main thing that our organizations are designed to do is sort of manage and make the best possible use of non-codifiable knowledge, here comes AI that can do that kind of knowledge at scale. That should lead to reorganization. And the essential idea of this paper is we want to understand how these reorganizations happen, and we think we need to understand these reorganizations to understand the effects of AI in the economy. Okay? So what's the outline of the talk? The first is the first part of the talk will have no AI, actually. I'll just tell you about this literature. I'll just give you a canonical model of the knowledge economy. This has been developed for the last 20 years. So we'll have nothing new to say here, just me telling you about these models. Okay? Now, the key about these models is that production relies on cognitive non-codifiable knowledge. And as a result, organizations form to make the best possible use of knowledge. Okay? And I guess one of the first messages I want to, or we want to give is this idea that this should be an important model for us to think about AI. Okay, so this is the first thing I'm going to do, but there's not going to be AI there. Once I've done this, we'll do the second message, which is, okay, how do we introduce AI here? Okay, and that's going to be the most intricate part of the talk, because I want to tell you how we've thought about introducing AI in this model. It's essentially going to be a technology that can automate knowledge work. Then I'll give you the economic impact of AI. Once you model AI in this way, what is the economic impact of AI that is autonomous, like humans? Then we'll go to the role of AI autonomy. What happens if we regulate the autonomy of AI, or for technological reasons, AI cannot be autonomous? How does that matter? And finally, I'll provide the rationalization of the seemingly contradictory evidence that we've seen a minute ago. Okay? Okay, so let's go. This is the knowledge of the model of the knowledge economy. This is the same baseline as these other papers. And again, I'm not going to do anything new here. I'm just going to tell you about the model that we think is useful to study AI later. Okay? So how's the model? There's a unit mass of humans. Each human is endowed with a particular level of knowledge, Z. And I want you to think of this Z as the fraction of problems that this individual can solve. You'll see that in a minute. For today's illustrations, I'll give you illustrations only, not general results. So we'll go with uniform distribution. Actually, in the papers, we have general results that hold for all distributions. But for today, just think of humans are uniformly distributed in this unit interval. There's competitive firms. There's free entry. There's so it's just going to be a competitive economy. There's not going to be any externalities, any information asymmetry. It's just plain vanilla competitive economy. The role of the firms is going to be the organized production. What can firms do, or how does the production function look like? Well, if you want to produce, you'll have to hire workers. What happens when you hire a worker? Well, she'll dedicate her time and knowledge to pursue a particular project. Okay, I want you to think of, there's a pool of ex-ante identical problems out there. You want to produce, you have to hire a worker and have her pursue one of the projects. They all look ex-ante identical. Once you start pursuing a project, however, if you want to conclude that project and produce 1 unit of output, you'll have to solve a problem, or the worker will have to be able to solve a problem. The difficulty of the problem is going to be uniformly distributed. And this is why you can think of Z as the fraction of problems that the worker can solve. So if you have a worker with knowledge Z pursuing a project with probability Z, she'll be able to actually solve and produce 1 unit of output. If she cannot solve the problem, she produces 0 units of output. When can she solve the problem? When her knowledge is larger than the difficulty of the problem. Now, that's not the only thing that firms can do. Firms can also hire a solver, which is you can think of as a manager. And the role of the manager will be to help the workers in the firm who get stuck. All those workers who find a problem that is more difficult than they can solve, they can now ask the solver. Okay? Before giving you more details, let me give you the main idea of this model. The idea is that firms will have a hierarchy, and this hierarchy is designed to shield the solvers from routine work. So there's going to be certain individuals who endogenously become solvers. They don't do routine work. They don't spend their time doing routine work, pursuing projects. They just specialize in helping with the difficult problems. Okay, and this is what's in the literature is called management by exception. There's this quote by Alfred Sloan way back saying, we do not do much routine work with details. They never get up to us. I work fairly hard, but on exception. So it's a theory of hierarchical organizations where the hierarchy determines what kind of things different people do. Those who are at the top of the hierarchy are actually solving the exception, solving the hard problem. Okay? And also it's a model of tacit knowledge, because if you can, what Alfred Sloan is doing here, or what the solver in this model is doing, is not designing a list of how you should do whatever comes up in production. What's happening is that the solvers are helping case by case, because they cannot tell what they know to the workers. They can only give solutions once the problem comes up. Okay? So this is very much a model of tacit knowledge or non-codifiable knowledge. Okay, with all these, let me continue the description of the model. So the production workers can ask the solver for help when they get stuck. That will have a cost, of course, and it's going to be a communication cost. Okay, so there's going to be asking for help consumes 8 units of the solver's time, regardless of how difficult the problem is, regardless of whether the solver knows how to solve that or not. So if the worker asks and the problem is more difficult than the solver's knowledge, then the solver cannot help either. Okay, but in any case, every time the worker asks the solver, it will take 8 units of the solver's time. So I want you to think of what kinds of firms can occur in equilibrium. Essentially, there's going to be 2 types. You can have firms that have only one hierarchy, one layer. And as a result, there's just workers trying to produce. If they cannot, they don't produce. And there's going to be hierarchical firms where there's a bunch of workers and a solver on top. The workers, each of them pursues a project independently. If they can solve the problem, they don't bother the solver. If they cannot, then they ask the solver. If the solver knows how to solve that problem, there's communication, and the worker solves the problem using the solver's knowledge. A couple of remarks. You can see how I'm depicting homogeneous knowledge at the bottom layer. That's actually without loss, because there's going to be positive assortative matching in equilibrium. So you could allow for firms to have different knowledge at the bottom. It's not going to happen in equilibrium. Second, you could get creative and say, wait, but if layers are useful, why don't we have a 3rd layer? And that's a good idea. We're going to assume a maximum of 2 layers for simplicity. Some papers in the literature allow for more layers. We think we get the main forces with just 2 layers. Of course, the referees asked, and we've generalized some of the results. But let me just focus on 2 layers for now. There's some extensions in the paper. Good. So, yeah.
The solver, the set of problems the solver can address, is that similar or different than what the production worker addresses? I mean, in terms of their capabilities.
Good. So the primitives here are, there's humans, each with their own knowledge. They are all just They have one unit of time, each have their own knowledge. Now, endogenously, these humans match in organizations, and the solvers are going to be just handling problems. And which problems are they handling? The problems that the workers don't know how to solve. But who is a worker, who is a solver? It's going to be an endogenous object. It's not like some people are born solvers, some people are born workers. So the firms endogenously will form, and they will match different individuals. So which problems do you see is determined endogenously in equilibrium. It depends on how firms hire you. If, for example, if you are in a firm with very good workers, you'll only be seeing very hard problems because these workers are very good. If they ask, it means the problem is very hard. So we're going there. Now, okay, so this is the model. Now, how does the equilibrium look like? We're going to be looking at the competitive equilibrium, which is, because there's no asymmetries of any sort, no inefficiencies of any sort, this is just the same thing as efficient output. So what does the equilibrium have to tell us? It has to tell us three things. First, it has to tell us occupations. And this is related to what I was saying. Out of, essentially, tell me your knowledge, and the equilibrium has to tell you, are you going to be a worker, meaning you're going to be doing routine work with access to a solver? Are you going to be an independent producer, just doing routine work but no access to a solver? Or are you going to be a solver? So this is an endogenous object. What kind of occupation are you going to be? Now, there's going to be something called occupational stratification in equilibrium, which means that who are going to be the solvers are going to be the most knowledgeable individuals. Who are they going to be assisting? The least knowledgeable individuals. That's what we're saying here. Why is that? Well, if someone is going to specialize in solving problems, it better be those who know most. That makes quite a bit of sense. So that explains why the most knowledgeable are the solvers. Why is it that the independent producers are going to be the ones in the middle? Why is it that those who receive assistance are the least knowledgeable? It's because if you're going to assist anybody, you want to assist those who ask easy questions, because the likelihood you can help them is higher, right? And that explains why the least knowledgeable are the ones getting assistance, because they are the ones who are asking very easy questions. It's sort of very low-hanging fruit there. So that's that, occupational stratification. The second one is the equilibrium has to tell us a matching function, has to tell us which workers match with which solvers. And the equilibrium will have, as I said, positive assortative matching. So the good solvers are more valuable to the good workers. Why is that? Because the good workers ask very hard questions. If you match the good workers with the bad solvers, those solvers don't solve anything. So you want to match the best solvers with the best workers. Right? That's essentially what this is saying. There's, of course, a market clearing condition. Helping time demanded by a given set of workers has to be exactly the same as the helping time supplied by the solvers they're matched to. We don't have to worry too much about that today. The wage schedule essentially has to tell us the prices in equilibrium. There's only one production factor here, which is human time. So, and knowledge. So tell me what's your knowledge, I'll tell you what's your wage. And that is going to be determined by the zero profit condition of firms. So this is, the equilibrium will have to tell us these three objects, okay? Let me give you an example. I said I would go for example. So instead of characterizing things in general, we'll work with an illustration. Before that, you can notice that if the communication cost is small enough, it doesn't make any sense to have one-layer firms. So let me get rid of that case for a minute. So we'll just focus on H small enough, meaning there's no independent producers pre-AI. Post-AI, there might or might not be, but pre-AI, there's not going to be independent producers. Okay? So let's go for the example. And this example is uniform distribution of knowledge. And H is a half, meaning when a worker asks a solver, it takes half the time of the solver. Does that mean that each solver can only have two workers? No, it does not mean that, because workers, they not always ask the solver. So if you have very good workers, you can have many more than two workers. You can ask two questions, but you can have many workers because workers don't ask always. We're good? Okay, so this is the equilibrium in this case. So what do we have? In the x-axis, we have knowledge. Our humans are uniformly distributed in this example here. We have occupational stratification, meaning there's a cutoff of knowledge. If you're above that cutoff, you're a solver. If you're below that cutoff, you're a worker. Again, this is an endogenous object. It's not that they were born like that. It's that the equilibrium allocates them like that. Okay? Firms find it optimal to hire people in this way. So there's occupational stratification. Then we have a matching function that matches individuals in W with individuals in S, and it's positive assortative matching, meaning this is increasing. The best workers are matched with the best solvers, and the worst workers are matched with the worst solvers. Okay? Positive assortative matching. Finally, wages. We have the 45-degree line here. That would be the wage of everyone if they were in an one-layer organization. If everyone is working by themselves, there's no matching. How much you produce, your expected output. What's your expected output? Your knowledge. Okay, that's the probability that you can solve on your own. That would be, if we didn't allow two-layer firms, your output would be the 45, your wage would be the 45-degree line. Once we allow for two-layer firms, everyone's wage is higher than that. That suggests that two-layer firms are efficient. That's why they form. The wage function is increasing as it should be. It's more knowledge is valuable, so you'll get more wage the higher your knowledge. And it's also convex. And the convexity is interesting because it's a result of positive assortative matching. So when you're a better worker or a better solver, not only you can solve more problems on your own, but you're also better matched. And that leads to a convexity in the wage function. So this is the model. Okay? Any questions about the model? Okay. So now comes our contribution, which is to take this model. I mean, the first message is we think this model should be used to study AI. We think there's a lot to do here. So we set about doing it. Okay? How do we do that? Well, there are three key developments that guide our approach. And this is the part where I expect. So I hope everyone is on board that this is a potentially useful model for studying AI. I expect a lot of you to disagree with me with the exact way in which you do it, but that's fine. I hope. So I expect that a lot of questions that you ask, I'll answer, yeah, that's a good idea, let's do it, right? There's a lot left to do, but let me tell you how we do it. So what are the developments that guide our approach? The first is this rise of general purpose AI foundation models. Okay, so we don't want to think of AI as some technology that every firm will gather their own data and they'll train their own model from scratch. We want to think of these foundation models that you can take off the shelf and use. That's the first part. We'll think of these as digital brains, very general purpose, akin to organic brains, but some ways that you can grab and use. The second is these ambitions of autonomous AI agents. We're not thinking too much about chatbots. We're thinking more about AI agents that can do more than that, can go out in the world and do stuff for you. Third, and most important, I think, is that AI can perform this kind of knowledge at scale. And this at scale has many meanings. Let me bring it down a little bit. In two ways. So the first one is, this is, I think, the most fundamental point of the paper, which is artificial intelligence is different from human intelligence because machine time is not tied to any digital brain. I can have some computing power, and at every point in time, I can decide which system I use. That's very different from human intelligence. So I cannot come here today and say, you know what, Eric, I like your brain more than my brain. So let's use my time with your brain. We cannot do that. As a result, I'm stuck with my brain. I'm employed in equilibrium. He's employed in equilibrium. We have different knowledges. And we just cannot do this kind of trade. As a result, we have this huge distribution of knowledge in society. Everyone is employed. With AI, it's very different. You have these different digital brains, but we all can choose to pick one if we want. That makes a huge difference, we think. In particular, all compute can be used with the best digital brain available. If there is one digital brain, that's another question, but you can think, oh, there's these different digital brains. If there is a best one, we can all use it. That's very different from human intelligence. The second one is machine time is large relative to human time. And we'll take that to mean in our model that the human AI interactions, we take human time and machine time, they're going to be constrained by human time, not machine time. So this is the philosophy behind it. Now let me tell you how we actually do it. So, and this, I have to say, it's a benchmark. Later we'll consider different types of AI, okay? But we think as a benchmark, this is useful. So what is AI? Is it going to be a technology that is available to all firms for free? Meaning the actual weights. Doesn't mean that using is free, but it's sort of a publicly available technology. What can the technology do? It can mimic a human with certain knowledge, the AI.
Question. Why the focus on non-codifiable knowledge? I mean, it seems like we could perhaps debate about structured versus unstructured, but it seems like a lot of what AI is doing is actually on codifiable knowledge. Why focus on non-codifiable?
Good. So I would argue that automation of codifiable stuff, we've seen for a long time. We have data about that. We have models about that. We understand it quite well. We think that what is fundamentally new about AI is the non-codifiable part. That's why we're focusing on that. I agree with you that AI is doing many other things. I think that is much well understood, much better understood than this part. That's why we're focusing on this part. So for example, AI will do better translation. AI will do a lot of things that you can think of as codifiable. We're focusing on this part because it's the new one. Yeah.
Follow up that. The follow-up question to that is that, well, if you're focusing on non-codifiable knowledge, and by the fact that it is engaging with AI, it becomes codifiable, that poses a contradiction.
You would think?
I would. How would you think about it?
Yeah, it's a good point. It's a point I've actually talked about with these two gentlemen right here, which are the experts on this. So let me see if I can explain this. But what this paper suggests, and we touch about it in certain part of the paper, is that we've had this traditional distinction between codifiable and non-codifiable. AI makes this distinction a little bit blurry. Why? Because once AI can get certain knowledge, it sort of codifies it, but only for the machines. So it becomes knowledge that is codifiable for machines, but you give me the OpenAI weights, and I have no idea what to do with them. You give them to computing power, it knows exactly what to do. So you're right. You're right. You would seem it's contradictory, but it's not. What happened is that the introduction of AI makes this distinction kind of not so kosher anymore. Good. Okay, so how do we actually bring down all these ideas to the model? It's a technology. What is AI? A technology that is available to all firms for free. That's sort of the standard assumption in economics. There's this technology, we can all use it. This technology mimics human knowledge with certain knowledge AI. So you can think of AI being very good, but also very bad. Okay, I'll give you different examples. And the key or the catch is it requires computing power to run. Okay, we'll normalize the units of computing power for simplicity to you need 1 unit of compute to mimic 1 human. Okay, I know that you just have to do a conversion. So I'm not going to talk about tokens or anything like that. Finally, there's an endowment of compute. There's an amount of compute new that we'll think of large because of what I said before. What does this mean? It means if we had these were our 2 different companies pre-AI, the 2 different kinds of companies we had pre-AI, now we can have 3 others. What are these 3 others? Well, the first option is you do independent production, but you use AI instead of humans. The second option is you have a hierarchical firm, and the AI is used in the bottom layer. And the third option is the same, but with AI used in the top layer. Right? So these are the 3 logical possibilities post-AI. I'm not saying this is going to happen in equilibrium. I'm just saying this is what can happen in equilibrium. Okay? Why not have fully automated 2-layer firms? Well, because if AI doesn't know how to solve a problem, it doesn't make any sense to ask another AI because they have the same knowledge. And that's the key. Why humans have this heterogeneous knowledge, but AI doesn't? It's this idea of scalability. We're assuming here in the background that there is a best model, and then we're using all compute with that best model, right? That's something that is completely different from humans. You cannot think like that with humans because of what I was mentioning before. Okay, what does that? What do we mean by the amount of compute mu is large? It means that some compute must be used in independent production. There must be some compute here. In other words, if you try to match all computing power with humans, you just don't have enough human time for that. There's not enough humans to match with all compute, so some of the compute has to be used for independent production. As a result, this spins down the rental rate of compute in equilibrium. It's going to be ZAI. And because AI, one AI agent or one unit of compute is a perfect substitute with a human with knowledge AI, that also pins down the wage of humans that have the same knowledge as AI. That's going to be their independent production expected output. There is a question?
I would just comment. This is all great. I mean, in terms of a particular model, but there certainly are lots of different sized AI models with lots of different capabilities out there in equilibrium. So that's a particular assumption. I don't think it would be that hard to extend your model to have heterogeneous AI, and you would get that other category as well.
Yeah, that's a great point, of course. We've actually done the extension. Okay. The first observation is, suppose you have different models. They all take the same compute to run. It just one knows how to solve more problems than the other. Then you're back in this case. You only use the one that knows best. Your point is good though, because we know there's some models that take less compute than others. So there's sort of models that know how to solve less, but they also require less compute. So we've worked out that, and in equilibrium, you might have 2 or 3 being used in equilibrium or more.
I mean, it wouldn't be hard to make an argument that there's more heterogeneity between some of the very, very small models and some of the very big models than there is among humans. And maybe that would flip some of your later results. But
it seems like there's a good other paper to write.
Exactly. Next paper.
Yeah, next paper. Now, so the point is, no matter what it ends up being the right way to model this, it's going to be very different than humans because of the idea that compute is very portable to different digital brains, human time is not. So it's going to be very different than what we already know. How to do it is another question. We've gone to the extreme of saying, let us assume there's the best AI model out there. We'll all use all compute there. But it's, of course, a point well taken. Good. Another opportunity for interesting work to be done here that we haven't done yet, and I invite you all to consider, is we have this mu parameter here and this ZAI parameter here. These we take as exogenous. There's a lot of interesting I/O of AI to be done here. Where does this come from? Where are the incentives? We haven't done it. We think it should be done. Good. So what does the equilibrium look like in this case? Well, same objects as before, right? It will have to tell us the allocations or the occupations, the matching, and the wage schedule. Now, the only thing is now the occupations, I'm putting some subscripts because we want to distinguish between who's matching with AI and who's matching with other people. Okay, so WA are workers matching with AI solvers. WP is workers matching with human solvers and so forth, right? So but it's the same as before. The new thing is now we have this mu W, how much compute will the equilibrium allocate to AI doing routine work with assistance, how much compute will put to independent production, how much compute will put to solvers roles. The matching function, same as before, has to tell us how we're matching the humans. We know people in WA are matching with AI, people in SA are matching with AI, so we need to know the matching from WP to SP. And the prices are now the same wage schedule. So wages, give me your wage, give me your knowledge, the function will tell you your wage, and the rental rate of compute. Okay, the equilibrium will have 4 key properties that we use. Same 2 as before, plus 2 new ones. First, occupational certification as before. This is same idea as before. Who is providing assistance? The more knowledgeable. Who is receiving this assistance? The least knowledgeable. Same intuition as before. The second one is new and gives us a lot of traction. Once you know where AI is, you know there's not going to be solvers below with knowledge below AI, and there's not going to be workers with knowledge above AI. Why is that? Well, because we're introducing this huge mass of AI agents and knowledge AI, so many that there's going to be independent producers there. Once we know there's independent producers that knowledge the AI, by occupational stratification, we get this result. It's really just the AI being used at scale that drives this result. Third result is same as before, positive assortative matching. So the matching function between humans is increasing. And who, out of the workers, which workers are matching with AI? Which workers are going to use AI as a solver? It's going to be the least knowledgeable ones. Why is that? Because if AI is a solver, it's the least knowledgeable solver. And by positive assortative matching, the least knowledgeable solver matches with the least knowledgeable workers. Similarly, which solvers, if any, are using AI to do routine work, it's going to be the best. Why? Because we know that if AI is a routine worker, it's the best worker. The result is matched with the best solvers. And finally, and this one took us months to figure out exactly the solution to this. How is AI used in equilibrium? We've worked it out, and then we realized it's not really very useful to know. I mean, now it's buried in the online appendix somewhere. But what really is important to know is the following, which is very easy to prove. If AI falls in the pre-AI worker camp, so if the knowledge of AI is such that pre-AI will be a worker, then AI is used as a worker for sure, possibly as a solver. And that's the part that requires some work, but it's not really super necessary to understand when. If AI falls in the pre-AI solver camp, meaning pre-AI, this knowledge would lead you to be a solver, then AI is necessarily used as a solver, possibly also as a worker. Okay, so let me show you how these translate to our nice illustration from before. So we start with this pre-AI equilibrium. Now we want to understand what are the effects of AI on this equilibrium. Okay, let's start with the basic AI, somewhere here. We know a lot of stuff already. So we know that the wage at the AI will have to fall down to a 45-degree line. That's the scalability part. And we also know that there cannot be workers above the AI. So all these guys here who were workers will have to find another occupation. They cannot be workers anymore. This is how it looks like in the end. So what we end up with in this example is the wage at the AI falls to a 45-degree line. Everyone who's less knowledgeable than AI is still a worker, but is matched with much worse solvers. These guys previously were matched with very good solvers. Now they're matched with these solvers right here. And from here on, essentially from half of the knowledge up, these guys are just renting compute, or they're matching with AI routine workers. So what's happening here, when AI is basic, when AI is not very good, all the most knowledgeable ones essentially just match with AI. They win a lot as a result because AI is relatively cheap. As a result, the least knowledgeable workers are really screwed in this case for two reasons. One, they are directly competing with AI. Second, they are left with much worse solvers. The result, they lose. Okay, this is a basic AI case. Yeah.
What you're saying is that the workers above the AI either becoming independent contractors or solvers now.
Exactly.
So some of them get promoted in a sense.
So what's interesting is, yes, they get promoted to problem solving, but their marginal product goes down. So
depending on whether it looks like some of them goes up.
Yeah. So it's not a general result, but yeah, the general result here will be if AI has the knowledge of a pre-AI worker, the best workers move to problem solving. That does not mean that their marginal product goes up. It's an independent. Good. Now let's take the other case where AI is much better. AI has the knowledge of a pre-AI solver. Again, we know a lot of stuff already. We know that the wage at the AI will have to go down to the 45-degree line. And we know that there cannot be solvers below AI. So all these solvers will have to demote it, if you want, to routine work. That doesn't mean they necessarily lose, but all these solvers right here cannot be solvers anymore. And this is how it looks like. And this is an interesting case where AI here is being used in all roles. The most knowledgeable guys are using AI for routine production work, and they still win. Why? Because now it's this AI system that is very good, relatively cheap. They still can leverage their knowledge very well. They love it. The least knowledgeable guys, the difference now is that the least knowledgeable guys also are happy with this, because they say, well, now this thing is not competing so much with me, and I can use it for problem solving. It's a relatively cheap manager, if you want. So now all the least knowledgeable guys start winning. And those who lose are just the ones who are very close substitutes to AI. Okay? Good. So once we see these results, we see this idea that, well, and the general results are, well, there's always winners at the top because of the reasons we've mentioned. In order for there to be winners at the bottom, we need that AI is good enough. Okay? Now, you might ask, well, this is a benchmark where the AI can do exactly the same as humans. They can pursue projects, they can solve projects. What if, for technological reasons or regulatory reasons, we say AI cannot pursue projects anymore? It can help you, it can help humans solve stuff, but it cannot actually go out in the world and pursue projects independently. Okay, that's the question we want to continue with. So we focused on autonomous AI, which can do everything just like humans. What if we consider non-autonomous AI, which can only be a solver? You cannot say, okay, I'll hire this AI agent, go pursue this project on your own, tell me if you face a problem. So essentially what we're saying is these were the autonomous AI possible firms. What if we don't allow this one, because here AI is pursuing projects independently, and we don't allow this one? We only allow AI to be used as a solver. When you are stuck, you can ask the AI. Okay. What are the effects? Well, this is essentially a picture I was giving you before with autonomous AI. Here is the AI I have. All the least knowledgeable guys lose. Why? Because, well, they are worse matched than before, and the AI is competing with them. The most knowledgeable win. That's the story I've told you before. So introducing autonomous AI in general, unless it's very good, it leads to much higher labor income inequality. What if we keep the AI where it is, but we don't allow AI to be autonomous? The picture is as follows. What happens here is the winners in this case are the least knowledgeable, and the most knowledgeable don't necessarily win, and in general lose. It's not a general result, but the big advantage that AI provides the most knowledgeable disappears. Why is that? Essentially for two reasons. What's happening now when AI is not autonomous is that AI agents are not a perfect substitute with the humans, so they don't compete directly with them. That's the first one. The fact that AI cannot pursue projects means that it's not directly competing with with the individuals, humans who are not so knowledgeable, and they are pursuing projects. That's the first one. Second, you're putting a lot of constraints on how you can use computing power in the economy. As a result, the price of compute in equilibrium goes down. What does that mean? It means that it's much easier, it's much cheaper to use AI as a solver. Who benefits from that are the least knowledgeable. So when you prohibit a lot of use of AI, you don't allow AI to be autonomous. In this model, actually, the rental rate of compute goes to 0. And now the least knowledgeable say, great, I have this free advisor. And who wins from this free advisor are the least knowledgeable. Why is it the least knowledgeable? Because the most knowledgeable, why would they want to ask a free advisor that knows less than them? They have no use for it. The only reason the most knowledgeable were winning is because they were saving time with the AI pursuing independent projects for them. But once you don't allow that, they don't see any value, and actually, as a result, they tend to lose. Okay? So there's a trade-off here. If you're thinking about regulating autonomy, there's a trade-off. Aggregate output is larger with autonomy, but labor income inequality is also larger with autonomy. So we might want to be careful. There's a question?
In the non-autonomous scenario, what's the difference between AI versus other technological tools such as Google?
Yeah, you could think The non-autonomous AI case, you might think of it more as what we have right now with the chatbots, with LLMs and so forth. The difference that with the previous technology, like Excel and so forth, or software programs that we had before, is the fact that in this case, AI can help with this non-codifiable knowledge. We're again back to the idea we're considering here industries where you require non-codifiable knowledge, and Excel was not very useful for that. Now, your favorite foundation model is useful for that. But you're right, you're thinking in the right direction. Thanks. Good. So now we're back to this seemingly contradictory evidence, right? So we have certain papers, one by Eric forthcoming at QJE, the first one, suggesting that AI benefits the least knowledgeable the most. But then there's other papers that in other settings with other sort of AI tools suggest the opposite. What might be happening, of course this is tentative, arguably the first set of papers are focusing on AI agents that can assist humans with problem solving. The second sort of papers are more looking at AI agents that can actually do some of the routine work for you. And that makes a huge difference, right? So what might be happening is that we're not controlling, when we compare across these different experiments, we're not controlling for the autonomy of AI or the ability of AI to do routine work for you. And that might or might not be the key. So let me conclude. I told you that was our goal. We want to organize the discussion. We want to guide empirical analysis. We want to guide policy. What is sort of the takeaways here? I did a bad design, and now the line is just, but it's okay. Now, how is AI different from previous automation, and why this matters? Well, AI can alleviate a major bottleneck in the economy, which is all this work that requires non-codifiable knowledge, right? We think this is a big deal, and we should look into this. Why? Because non-codifiable knowledge, once you require that, you require organizations to make the best possible use of knowledge. So AI is likely to lead to a reorganization that we want to understand. What determines who is complemented and who is substituted by AI? Well, it depends on the autonomy. If it's autonomous, it mainly benefits the most knowledgeable, unless it's very good. If it's not autonomous, it mainly benefits the least knowledgeable. Guide empirical analysis, the potential explanation for this seemingly contradictory evidence is the autonomy is not kept constant across the experiments, which is natural. Can we rationalize this evidence? Well, it would be nice to collect in new experiments, not only how intelligent the AI is or how emotionally good it is, but also the action quotient, if you want, like how much can it do on its own. Finally, what are the effects of regulating AI autonomy? Well, there's this trade-off between aggregate output and inequality. You might find that if you want to regulate autonomy, it's good for labor income inequality in the sense that it reduces it, but it also leads to much lower output. Finally, and I'll finish with this, so you might or might not like the exact way in which we've modeled things and the exact calls we've made. We've made a lot of calls in how to model this, but I think the essence of the paper should go through, and we're very excited about this, which is this combination of two observations. AI can automate work that relies on non-codifiable knowledge. That's a big deal. Why? Because non-codifiable knowledge has this special structure. It's a major bottleneck in the economy, and it requires organization. You combine that with AI scalability, we think this should lead to a reorganization of the economy. And we are all about trying to understand this reorganization. It's the first paper we write on this, but we hope many more are going to be written about exactly what about this reorganization is important. And I'm happy to chat about it. Thank you so much.
Thank you. So we have 10 minutes or so for questions. Anyone? Let me ask the first one, which I'm going to, you and I had a fun conversation just beforehand. And this is a one-dimensional spectrum of intelligence. And we talked about making it multi-dimensional. And you've already got some pretty cool results when you go to 2 dimensions. Without having the benefit of being able to show them on the screen, I don't think. Just tell us a little bit about that.
Thank you. Thank you for the question. Yeah. So right after finishing the first draft of this paper last summer, well, actually not the first draft, but after submitting it for the first time, we said, this baseline is great, but once you start thinking about AI, the multi-dimensionality of knowledge is crucial. And here we have a baseline. The literature, for one reason or another, has focused on one dimension, So we really, in this paper, we forced ourselves to not change the baseline, and we stayed with that. But the first thing that we thought would be interesting was to think about, okay, what about having as the pre-AI benchmark multidimensional knowledge? So you have, what's the next step after 1, 2? So now we have 2 dimensions. And now the interesting thing, and we were very inspired by Eric's paper on the Turing trap, which is about this idea of in which direction do you want to push this technology, right? You want to make it close to humans, different than humans, and of course, close to humans, make it more substitute. So we were really inspired by that vision, but we were asking, well, what can we use this model to sort of formalize that? So the main result is we're looking at what is the effect of AI improvements in either dimension of knowledge on labor income. And the result we get, and as a result of this, of what I'm just going to tell you, we call the paper the Turing Valley. So why do we call the paper the Turing Valley? Not only to hook Eric on this, but also because the result is the following. If you improve AI in a dimension in which it is less knowledgeable than humans to begin with, labor income goes down. If you increase AI's knowledge in a dimension which is already better than humans, labor income goes up. So this is very much in line with your paper on the Turing trap, but it gives micro foundations for it, and it shows very nice. I mean, next time you invite me, I'll present the full thing. But we think it's a very nice macro foundation for this idea, and it suggests when are humans more useful? Well, when the AI asks questions that are more friendly to them. When is that? When the AI knows a lot about the things that humans don't know. So that's the main idea.
Your mic already.
Great. No, I enjoyed the paper a lot. This kind of follows up a little bit on Eric's question. I'm wondering what happens if ZAI goes to 1? So what if they can solve all our problems? And maybe to get beyond human, what if humans are capped at Z equals 0.8 and the AI goes to 1? Seems like those cases are also kind of interesting. So you've probably thought about it.
Yeah, very good question. So if we keep humans in the 0-1 line, so there's there's a discontinuity in the equilibrium at ZAI equals 1. So as you are moving ZAI towards 1, there's always winners at the very top. Now, if you say, okay, now AI knows everything, now there's no more winners at the bottom. Everyone uses AI as a solver. So the result, there's this discontinuity there. I guess we haven't done it, but if you start saying, well, and this is, you said it at the beginning, and you're completely right. It's very related to this Turing Valley idea, because suppose humans are between 0 and 0.5. As you improve AI between 0 and 0.5, the effects are complicated on labor income. But as soon as you pass 1/2, any improvement on AI from there on increases labor income, right? It's the Turing Valley idea. So from that point on, better and better AI actually helps the labor income more and more. So yeah, these are good questions, of course.
Very interesting. I'm not familiar with this family of economic models, but I'll ask anyway. So when I think about your solver and your workers, it strikes me that AI solvers will have different characteristics from human solvers. And some of the interesting differences would be availability and time to solution. Which would, of course, ripple down and have impact on worker productivity. Another kind of thing that they might have, especially if we decide we're just going to use the best AI model for all the solvers, then we'll have highly correlated failures of the solvers. Are those things already accommodated because you're looking at equilibria, or are they things you want to deal with?
Yeah, these are great question. I think the first one we tried to capture in the idea that mu is large, and it's within the normalization of the units of compute. We're trying to capture a little bit, but more generally, let me take this as an opportunity to think, or to say, I think it's a great opportunity for collaboration between economists and computer scientists. So this is the first effort in this direction. And we're making a lot of, just as a benchmark, what would you say? Okay, the AI is going to be exactly like a human, just as a benchmark. But then I'm super excited to talk about discussing this with computer science in particular because there's a lot of differences between AI and humans. We have incorporated what we think is one of the things we think is crucial, but there's many more things to incorporate in these kind of models. And I want to learn how to do it. So perhaps we can chat more.
I have another question. Can you say, so this is very much focused on labor and labor income and the compute sort of, I guess there's a cost of it, but what would happen if you had or owners of compute and production of compute and returns to compute? Seems like that might become increasingly important.
Yeah, good. So you're right. In this paper, we're putting the lens on what happens on the labor market. But what we've done, even in this paper, is we started with, because it's non-codifiable knowledge, the literature has only studied essentially humans involved in this production process. What we're doing is, because of the AI revolution, we're saying actually now in this industry there's going to be, or in this sort of knowledge economy, there's going to be labor and also computing power. Now we're not taking any stance on who owns that computing power. It's humans, of course, and there's going to be returns on that. We're not asking where it comes from, what are the incentives to produce it. There's obvious things that you could say about that, but thinking about it more deeply is something it's completely open to do here. There's also an issue of capital income. In this model now, in post-AI, there's capital income as well as labor income. We might want to think about what is the labor share and how. And the issue of incentives, we're very much aware, incentives to develop the technology, depending on which objective you have. And that's why also we wrote the Turing value, because that paper is already asking a little bit more about what happens if you improve AI in this dimension, what are the capital returns, what are the labor market returns. And so we're getting into that, but there's a lot to do there.
Yeah, this is a good base. There's so many different directions you can take this model, and you've already done some of them, but I'm especially based with Chad's world where, the AI can do more and more, then it seems like maybe that you talked about what happens to labor income inequality, but maybe the more important thing is if labor income becomes less important, then where's capital income in a lot of models, that might be much more unequal.
Yeah, that's completely right. Completely right.
Well, we're out of time, so thank you very much for the presentation. Fascinating. Lots more. I bet you some of the people in this room will go further. And as we have a screen here, the next speaker, is that going to be a special time? Wait, is it? I thought it was on Thursday. Thursday the 13th. Yes. So Thursday the 13th is Diana's special time at 5:45, talking about her new book, The Measure of Our Progress. So hope to see you all then. Thanks very much.